Today's method of integration for our techniques is going to be using partial fractions to integrate. So fractions, are rational functions. When we're talking about algebra, we're talking about rational functions that are fractions. And so if we're using partial fractions, we first want to know what partial fractions are. So a partial fraction is a rational function that you are decomposing. You're splitting it apart. Essentially what you're doing is you are undoing the common denominator. You're like splitting it into what it could have been before you got a common denominator in the problem. So I'm going to say partial fractions are decomposing rational functions into sums of simpler rational functions. So instead of having the big complicated rational function, you're going to say, all right, if I split it into what the two fractions were that added to be it in the first place, then that would make the problem a little bit more simple. It would make it easier to integrate because we'll have something more simple to integrate. So when you're doing this, this really depends on factoring the denominator. All right, so the process that we use for decomposition of rational functions first, before we're going to see if we can do partial fractions using the method of factoring the denominator in like a long process. Before we do that, we're going to check to see if long division is possible. And we're going to use long division anytime we see a rational function that is improper. And what that means is that the degree of the numerator is greater than or equal to the degree of the denominator. So an example of this would be that problem that we did on page 521 of the Larson book. It was number 15, and we ended up needing to integrate t squared over t plus 1, and we had a hard time with that. So we did long division to make to figure out another form of the problem that maybe looked a little bit more simple, and then it was much easier for us to integrate. So that's essentially what we're doing today, is we're just breaking things down. So second, if that doesn't work, if you can't do long division, then that means you have to start off by factoring the denominator. That's you figuring out what your denominators are going to be for each of the different fractions before you got the common denominator. And then after that, you're going to write a sum of rational functions where the numerator is 1 degree less than the denominator. And there is one exception to this, and the exception is if you have repeat factors. A repeated factor would be like, I factored the problem and it was x plus 1 times x plus 1 for the denominator. That would be a repeat factor because you have x plus 1 squared. All right, so first I'm going to give you a little example of what I mean by decomposing the rational function, and then after that we'll actually do one where we use it to integrate. So for example, let's look at the rational function 1 over x to the 5th plus x to the 4th minus x minus 1. So when I look at this, if I was trying to do long division to start with, I can't because this is not improper. The degree of the top of this rational function is x to the 0, right? So the degree of the top is 0. The degree of the bottom is 5. So it's not improper. So no long division. That means I've got to factor this. Since I have 4 terms, That means that my method of factoring is going to be by grouping. So between the first two terms, my GCF would be x to the fourth, and my leftovers would be x plus 1. Between the second two terms, my GCF is -1, and my leftovers would be x plus 1. So now I'm thinking of this as the first term and this as the second term. And the GCF between the first term and the second term is x plus 1. That's what I see that's in common, so I'll go ahead and take that GCF out. And then the leftovers between the first term and the second term would be x to the fourth and -1. So the x plus 1 factor is finished. The x to the fourth minus 1 is difference of squares. So that would give me x squared plus 1 and x squared minus 1. Now these two factors are finished, but this is difference of squares again. So I've got x plus 1, x squared plus 1, and then x plus 1, x minus 1. Okay, so now I'm going to think about all the different factors that I have. I have a factor that's x squared plus 1. This factor is quadratic, or it has a degree of 2. I have a factor of x minus 1. That factor is linear. It has a degree of 1. And then I have the repeat factor, x plus 1. So I'm going to write this as x plus 1 squared. And I'm going to say that this is a repeat factor. And so that it has a degree of 2. But we're kind of going to treat it like it has a degree of 1. We're going to kind of ignore that a little bit. Okay, so here is how you write these out as a sum of fractions instead. So my first fraction is a quadratic, has a quadratic in the denominator. I did not need that parenthesis. So we know that the degree of the numerator should be 1 less than that. So the degree of the numerator means that it has to have a degree of 1. It's going to be linear. So I'm going to write ax plus b. That's my little linear function there with variables to solve for the slope and for the y-intercept. My next denominator is going to be linear. So my numerator would, if linear is a degree of 1, then my numerator has a degree of 0. That means I'm not going to have an x up there, I'm just going to have a number. And then for the last factor, we actually write this one twice. We're going to use x plus 1 and x plus 1 squared. Oh my gosh, every single time. I don't really need to erase the parenthesis, but it annoys me that I'm not being consistent. Oh, actually, I needed it on that one. Goodness. Okay, so C, and then D, and then E. So even though this one has a degree of 2, since it is part of a factor that was linear, we're still going to have a degree of 0 on the top. So this is not ready to integrate. Obviously, I've got way too many variables in there, but I just wanted you guys to see how we could split this apart into a sum of different fractions. So if we look at this, what we would need to do before we said, oh, now I can integrate this side, is we would have to solve for A and B and C and D and E. We'd have to solve for all those before we were ready to do the next step. So this is a fairly complicated example. I just did this because I wanted you guys to see how we work with each individual type of denominator. So for us to actually integrate, we're going to do one that's much more simple. So for these examples, the instructions that they would give you is they would just tell you to integrate. And the first one that we're going to do is we are going to integrate 1 over x squared minus 5x plus 6. Now the way it's written right now, I couldn't do u substitution with this because I'd have to say the entire bottom of that fraction was the u, and I definitely don't have a du in that problem. And I can't split this apart. I can't do 1 over x squared minus 1 over 5x because you can only split the numerator. You can't split the denominator like that. So for me to integrate this, I am going to have to decompose it and write it as partial fractions. So I'm going to go ahead and factor the denominator. That would be x minus 3, x minus 2. And then I can write this as the sum of two fractions, x minus 3 under one, x minus 2 under the other. Both of those denominators have a degree of 1. So the numerators need to have a degree of 0. That means I get no variable in the numerator. All right, so now I need to do the step where I actually figure out what the a and the b are. So what I'm going to do actually is I'm going to just multiply this entire side of the equation by x minus 3 times x minus 2. And you can think of it a few ways. You can think of it as I'm doing this because that's going to help me get a common denominator. You could think of it as I'm doing that because I'm taking this denominator and I'm multiplying each side by x minus 3 and x minus 2, and that kind of cancels these out and moves it over to the other side. However you want to think of it is fine so that you can remember it. But what I'm going to end up with is when I take this and multiply it by the first fraction, the x minus 3's cancel. And I end up with a times x minus 2. When I take these two and multiply it by the second fraction, the x minus 2's cancel, and I end up with b times x minus 3. So now I'm thinking this is what I would have had on the top of my fractions after I get that common denominator. And so the top of my fractions, when they are all, when you combine all the like terms and multiply everything out, it's going to end up equaling 1. All right. So next I have to think, how could I solve for a and how could I solve for b? And we're going to be kind of tricky about this. I'm going to say let x equal positive 2. If x equals positive 2, then I have 1 equals a times 2 minus 2 plus b times 2 minus 3. My a term is gone because that's 0. So I get 1 equals b times negative 1. And so b is negative 1. To solve for a, I can go ahead and say let x equal 3. Then that leaves me with 1 equals a times 3 minus 2 plus b times 3 minus 3. My b term is 0. And so I have 1 equals a times 1, which is just a equals 1. So that means if I want to rewrite that original, here's my original integration problem. That's actually going to be 1 over x minus 3 plus negative 1 over x minus 2. So integrating this problem is exactly the same as integrating this problem. And this is quite a bit easier if you look at it. So let's go ahead and do that integration. I'm going to go ahead and break these up because my brain prefers that. And for this one, I'm going to go ahead and take that negative from the top and just move it to the front. So technically this is u substitution because it's not just a plain old x, but I know that the derivative of this is 1, so I'm not going to do u substitution because I'm feeling lazy. So I'm going to say that this is ln of x minus 3 minus ln of x minus 2 plus c. This is a fine answer. You can totally leave it as this. However, I do know that subtraction problems for properties of logs means that the two things are actually being divided. So I can also write this as ln of x minus 3 divided by x minus 2 with a plus c on the end. So both of those answers are good. All right, let's go ahead and do a second example. So we're going to do one that's a little bit more difficult, where the top is not going to be 1, it's going to have an actual function up here. So the first thing I want to think about is Maybe I could make the bottom be u, and then the top could be the derivative of u, but if you look at that, that's definitely not going to work. The other thing we can look at is if the top is the, if it's an improper fraction, because then we can use long division. Again, not the case. So we really do have to decompose these. That means we have to factor the denominator. So when I look at this, the first thing I see is that I have a GCF of x. That leaves me with x squared plus 2x plus 1. When I factor that, that leaves me with x plus 1 times x plus 1. And so we do have a repeat factor in here. So I'm going to go ahead and write down what this is. I've got the top, so 5x squared plus 20x plus 6 over my factors. And I'm going to rewrite this as a over x, b over x plus 1, and then I get my repeat factor in there. All right, so just like last time, we're going to multiply this side by that denominator. And so if I think about multiplying this by the first term, that's going to leave me with a. The x's would cancel, so it's a times x plus 1 squared plus b. If I multiplied these two together, the x would stay, and one x plus 1 would cancel, but the other one would stay. And then if I multiplied these two together, the x plus 1 squared would cancel, and I would just be left with x. So this part right here equals 5x squared plus 20x plus 6. Now we're going to solve for a, b, and c just like we did before. So first thing, if I let x equal -1, then I'm going to be able to get rid of one of my terms there, actually two of my terms. So I'm going to say let x equals -1, so I've got 5 times -1 squared plus 20 times -1 plus 6 equals a times -1 plus 1 squared plus b times -1 times -1 plus 1 plus c times -1. So I just went through for all my x's and plugged in -1. Now when you do that, this part here ends up equaling -9. That's gone, and then we get c times -1, or negative c. So that means that your c value is 9. Next, I'll go ahead and let x equal 0, because that's going to be pretty easy to work with, and that's going to help us get rid of this one right here. So I've got 5 times 0 squared, 20 times 0 plus 6, a times 0 plus 1 squared plus b times 0 plus 1 plus c times 0. All right, so that's nothing, 0 plus 1 squared, this is going to be nothing, that's going to be nothing. So I've got 6 equals a times 1, so 6 is a. All right. For the last one, there's not another number we can have that will cancel things out, but it doesn't really matter because now we know a and c, so we can solve for b really easily. So at this point, just pick a number that's pretty easy to plug in. So for my last one, I'm going to go ahead and say let x equal 1, because that's easy to plug in. So 5 times 1 squared, 20 times 1 plus 6, and then I know that a is 6, so I'm going to say 6 times 1 plus 1 squared plus b times 1 plus 1, plus I know my c value is 9, so 9 times 1. So not only did I plug 1s in for the x's, I also plugged the number in for a that I knew, and I plugged the number in for c that I knew. So 5 plus 20 plus 6 is 31. 31 equals, that would be 24 plus 2b plus 9. And then I'm going to go ahead and subtract the 24 over and subtract the 9 over, so that gives you -2 equals 2b, and so b is -1. So if we go back to our original problem, integrating 5x squared plus 20x plus 6 over, I'll go ahead and write x times x plus 1 squared, it's the same thing as the bottom. That's going to be the same as 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 squared. And I'm going to go ahead and split these up. So I've got 6 times 1 over x minus 1 over x plus 1 plus 9 and then 1 over x plus 1 squared. So these ones are going to be ln's. These are pretty straightforward. This one over here is actually truly a u substitution because of that squared right there. So I'm going to say u is x plus 1, du is 1 dx. So we don't need a number to come out in the front. But when I integrate this, I am integrating 9 times the integral of 1 over u squared, which is the same as 9 times the integral of u to the negative 2. So keep that in mind. Okay, so for this first one, I'm going to have 6 times ln x minus ln of x plus 1 plus, and then the integral of this would be negative 9 u to the negative 1. So that means I've got negative 9 over u. Yep, negative 9 over u, which is negative 9 over x plus 1. So here, I'm going to flip it over. So we've got 6 ln of x minus ln of x plus 1 minus 9 over x plus 1 with a plus c on the end. That is a fine answer. The other thing is this is a subtraction problem and we can use property of logs to write it as 1. So I know that that 6 in the front is actually an exponent. So if I use my property of logs, that gives me x to the 6 over x plus 1 minus 9 over x plus 1 plus c.